Okay, let's begin by looking at how to calculate the pH of a buffer. So in this sample, we have a buffer of HCN mixed with its salt, potassium cyanide. Okay, and we're giving the Ka value. We're also given the pKa, which remember is just the negative log of the Ka value. Okay, so when we look at this, what we're going to kind of focus on is that HCN forms an equilibrium with H2O plus and the Cn negative, the cyanide ion. And I want to make an ICE table, initial change equilibrium value. So initially it is 0.25 molar HCN, okay, and then excuse me, there is also 0.170 molar of the cyanide ion, okay, initially there. Okay. H2O plus is 0. Okay. Now it's going to change in value, so we're going to see a minus x plus x plus x, giving us equilibrium of 0.250 minus x plus x and 0.170 plus x. So we do establish an equilibrium here in our buffer solution. So let's write the Ka expression for this. So we have H3O plus multiplied by the cyanide concentration over the HCN concentration, and we substitute in our values here at equilibrium. So we have x 0.170 plus x over 0.250 minus x. And all of this is equal to the Ka, which is 4.9 times 10 to the negative 10. Okay. Alright, so we have this. Now we can start evaluating and solving for x. But now it's going to lead us into a quadratic equation. So we're going to make an approximation here. What I'm going to do is I'm looking at this molarity, 0.250. See these molarities, they're in powers of 10 to the negative 1. And when I look at this Ka being 10 to the negative 10, I'm seeing a large difference there. So that's going to tell me there's going to be very, very little of dissociation of these X. There's going to be very few of these H3O plus, very, very few. So what I'm going to do here is I'm going to say that this change plus X minus X is negligible, or is so small that I can approximate it close to 0. Now when I do this, I am going to solve for X, and then I'm going to do a comparison of that X to these initial molarities to make sure that it's a very small percentage. Okay, we usually look for less than 5%. If it's not less than 5%, then we typically re-solve this using the quadratic. So this is going to look like x times 0.170 over 0.250 equals 4.9 times 10 to the negative 10th. Now I'm going to solve for x. So we have here 0.25 times 4.9 times 10 to the negative 10th, and then divide by 0.170. And we get x is equal to 7.20588 times 10 to the negative 10th. Okay. We'll only be allowed these two sig figs here, so I just made myself a little dash there so I would remember that. So that is x. Now when I compare x to 0.250, that is much smaller than 5% in the change. So I'm going to leave this approximation and say that it is valid. Okay. Now x is equal to H3O plus. So then pH being equal to negative log of H3O plus, I can put this in 7.20588 times 10 to the negative 10 and solve for pH. Okay, so negative log that answer, and it looks like I'm getting 9.1423 on and on. Okay. So it will end up being 9.14 as my pH. Okay.